Hi, everybody. I am Geoff Gerrietts. I'm going to talk to you about code review, revision, and technical debt. We'll see how I do with time. Yeah, so this is me when I was a little less hairy. I'm Geoff Gerrietts. I am, like I said, and I'm a development manager at AppNeta. I've been doing Python for 15 years. I've been a software developer for about 20. Over the course of my career, I've been a manager, a DevOps dude, a programmer, a webmaster, a technical writer, and maybe a couple other things. I don't know. Before I was doing that, I studied English. I like to joke with programmers about how writing poetry isn't that different from writing code, but now it gets real. Whoa. Come back here. So, as a field of study, English offers a lot of different specializations. Most of them involve a lot of writing. And if you go far enough, they involve teaching people to write. One of the things you learn when you study the teaching of writing is that direct instruction produces limited results. So probably everyone's seen a little bit of this direct instructions. It's a set of rules which, when strictly followed, produces a functional result. The result is rarely good, but it is functional. It's an open secret that the best prose never conforms to these rules. Teachers know it, and they say infuriating things like this. The best writing breaks the rules, but you need to know the rules to break the rules. Turns out that that's not really true. What actually separates expert from novice writers is not a superior understanding of the rules and when to break them. What separates experts from novices is that experts are much better at knowing how to revise than novices. It's not to say that the rules aren't useful tools for learning, but it's just not how the experts write. No expert writer is thinking, oh, I should choose a thesis and then build a topic sentence around that thesis. And at the same time, no expert writer is thinking, I don't need to do that. I'm an expert. Instead, they are revising. Okay? They are successively revising their language for better effect. So, for a novice writer, when you're, coming up in school, just committing ideas to paper is a serious struggle. Revisiting for grammatical correctness may be the absolute best you can hope to do. The rules help here by giving some clear goals to reach for and clear measures by which to judge their craft. But for the expert, before words are on paper, most of the sentence has already been composed in their head. They've tested the flow of ideas from the previous sentence to the next. Many of the word choices have already been tried and rejected, and they've settled on some that they like. Questions of grammatical correctness or paragraph construction never even rise to the level of conscious decisions. Subsequent revisions yield more dramatic and effective edits. Clauses are promoted to sentences, transitions are adjusted for impact and rhythm, words and phrases are replaced to better capture nuance. Incidentally, that's why so many low-level composition classes feature an outline, rough draft, final draft approach. The structure of composition pedagogy is to encourage the novice to continually revise their work. At higher levels, composition classes are actually workshops where everybody in the class looks at everybody else's writing and gives them feedback on it to further revise their work. So now you're thinking, great. If I want to write technical documentation, I know how to get better. But I don't want to. And I understand. Okay? I've done that for a living, and I don't want to either. I have to force myself to even write good comments. But just like learning to write is really learning how to revise effectively, learning to code is also really just learning to refactor. When we code, we are constantly revising the code we write. We jump back one or two lines to set a variable equal to 0 so that it's got a known start state. We indent several lines to create a loop. We set up a conditional. The process of coding is actually the process of revising our code until it does what we want. As we get better at revising our code, we develop the sense of code smell that steers our later instincts. So given this sentiment, you're probably starting to glean the broad outlines of my talk, but bear with me. I've got some more jokes in here and maybe some valuable insights too. Let's talk for a minute about what it means to progress as a programmer. It'll probably take a little more than a minute, but let's talk about how we learn to program. At the beginning of the coding journey, we're all apprentices. Our primary exercise is simply mapping logical flows onto language syntax, translating get a list of names into loop over user objects, joining first name and last name, and appending the result to a list, or later doing that whole thing in a list comprehension, is pretty much all we're focused on. Often, complex interactions require successive rounds of trial and error revision while we tease out the corner cases. Milestones might be learning idioms and language features. Idioms might include things like that list comprehension, which is not obvious at first, but those are very handy. Or it might be Python's not obvious way of spelling the do-while loop, or the else clause at the end of the loop, or even just the try, except, finally patterns for error handling. Idioms can also be domain-specific. Like in this example, these are the steps typically required handling a web request. These patterns are the very basic building blocks of programs. Apprentices are getting their collection started, filling up their bag of tricks. The next level up is the initiate. An apprentice becomes an initiate when their focus changes. The initiate has gained some fluency with idioms and language constructs, has a bag of tricks with a reasonable size to it, and now they're working not just on writing code, but they're working on writing good code. They're trying to select good abstractions. This makes the initiate the target audience for a whole crew of software rules. The canonical example is dry, which, in the unlikely event that you've never experienced it, stands for don't repeat yourself. It's broadly recommended, and probably everyone's heard it at least once. The rule says you ought to create a function or a loop where you see similar code. Some other rules I've seen are focused around the size of a code unit, which is the thing that we ought to be testing with a unit test. One guideline I've heard is that a unit should be no more than 100 lines. I've also heard 10, because apparently programmers love to do orders of magnitude math. Another guideline suggests that a unit should have a single purpose, which you can describe in one sentence with no conjunctions. The rule of three is a variation or extension of dry, where it says you don't create an abstraction the first time you see a thing, and you don't create an abstraction when you see a second kind of thing that's sort of similar. But the third time you see something that's pretty similar, it's fairly obvious that you know how to draw the right abstraction, right? Like our rules of composition, excellent code almost never conforms completely to these rules. But like our rules of composition, these guidelines are designed to help steer a programmer and help them level up their skill with abstraction. They offer guidelines for when and how to bump that level of abstraction without falling into over-engineering. Learning these rules won't make you a better programmer, and you probably won't decide to break them when you're good enough. But when selecting good abstractions is not automatic, using the rules to steer your decisions will help you understand what good abstractions actually are. And eventually, you'll automatically select good abstractions with no reference to the rules at all. That's when we start to think of you as a master. Masters have generally reached some conclusions about how and when to generate abstractions. Concern has risen to the level of subsystems and systems, of architectures and interfaces. Masters don't always agree, though. In fact, they often pick sides in the holy wars that perforate our industry. As masters increase their mastery, discussion generally is less about which of these is better and more about when each is appropriate. Of course, for some of these, there really is a right answer. I'll leave it as an exercise to the reader to figure out which is which. Just as the apprentice gains some skill mapping concepts to language, then the initiate learns to abstract those language constructs into reusable units. The master is learning to organize the units into cohesive patterns and interfaces. Now, my use of patterns here is an explicit nod to the immense body of OO literature on patterns, but it's also a more general meaning where small p patterns emerge in software and the master learns to arrange their constituent parts and arrange them with respect to other patterns. I personally place more emphasis on interfaces, but the two are really sort of opposite sides of the same coin. There are plenty of rules and heuristics for masters. I've listed a few here, although this is in no way exhaustive. Separation of concerns suggests that you divide your application into separate, non-overlapping components. The single responsibility principle echoes our previous statement about the design of units requiring an explicit focus. The principle of least knowledge suggests that components shouldn't know about other components' internals. Solid and GRASP are systems of complete acronyms that help you design OO systems themselves. Design patterns themselves are an orthodoxy. But as before, these tools are really useful for learning to design large systems, and they're useful for evaluating the design of large systems and for talking about the design of large systems. But at some point, the application of these rules ceases to be conscious thought, and you have become the guru. Now, sometimes when we say guru, we really just mean the smartest person in the room. But this kind of guru is like, if the room had a whole community in it, the guru would still be the smartest person in the room. Generally, these people see technologies in terms of trade-offs rather than silver bullets, and they can contribute to the conversation at technology's bleeding edge, at least on one of the edges. So that's the journey, from Padawan learner to Yoda. We start by learning to map concepts to code. We learn how to abstract those code fragments into reusable units. And then we learn to arrange those units into systems and subsystems with tidy interfaces. As we develop, the smaller abstractions become second nature, and we learn to work with the larger abstractions. In that way, programmers develop in a lot like programs do. We factor repeated lines into functions or wrap blocks and loops and conditionals. Later, we may recognize similarities between this code and some other code, and we might factor out another common abstraction. And still later, we may group those common abstractions behind some kind of interface. This is the behavior of coding, and just as it's the behavior of writing, constant small revisions with periodic larger revisions. So, advancement along our coder's journey depends on doing just that. We continually revise our logic to fit idioms until it becomes second nature to simply use the idiom. We continually revise our idioms into abstractions until it becomes second nature to generate good abstractions. And we continually revise our abstractions into patterns until it becomes second nature to design good systems. Learning the rules at each stage of our journey helps shape our revision, but learning to code is learning to revise. And learning requires doing the revision until our brains are reprogrammed to naturally produce good code. Learning the rules has value, but limited value in practical application. What helps most is reading code, writing code, and receiving feedback on your code. That brings us to the idea of code review, which I like. Over the years, I've repeatedly participated in and advocated for code review. Some software practices, they require a little bit of religion. We know it's a good practice because we know it's a good practice. But as software practices go, code review requires very little faith. The quantitative impact of code review on defect rate is well documented. It's also self-evident that code review reduces your organization's bust factor. But the aspect I like best is how it hastens professional development. All three of the things we need to get better are right there. Reading code, receiving feedback, and revising. But to make code review a mentorship activity, we need to be conscious of how mentorship is different from hunting bugs. When hunting bugs, the goal is bug genocide. When code review is about the bug hunt, you don't want to leave anything behind. It's scorched earth. And more importantly, all you're looking for here is bugs, places where the program won't function correctly. But when we review as a form of mentorship, we aren't just hunting bugs. We're looking for opportunities to better organize the expressed logic. The distinction can be fine, but it's very important. A bug is actually a defect that prevents correct functioning. Opportunities for improvement are mostly focused on the hygiene of the code base. Importantly, bugs are demonstrably wrong. Improvements are things that would subjectively make the code better. A lot of code reviewers have a hard time telling the difference. I don't think it's just an ego thing. I think anyway. We also do want to identify bugs when we're doing code review, but we need to identify potential improvements as well. And we want to make sure we're treating those potential improvements differently. So, high school composition teachers spend a lot of time correcting grammar and helping with sentence and paragraph structure. Collegiate corrections focus more on flow of argument, how linguistic choices emphasize and shade meaning. An instructor, or later a peer, is not expected to list all possible improvements they can think of, just the ones that seem most important or helpful. I mean, a high schooler who's working on paragraph construction simply is not going to make good use of feedback on how abrupt transitions can create emphasis. With code reviews, though, it often seems to go a different direction. Reviewers want the code being committed to be as close to perfect as it can be. So a huge laundry list emerges, some real bugs, some suggested refactorings. And what happens is learning and engagement go right out the window. The reviewee adopts a besieged mindset. Let me just do exactly what I'm told so that I can get this thing merged. So don't do that. Don't smother your programmers in issues. Instead, be relevant to the programmer's development. Meet the coder where they're at. Don't try to engage them in a discussion of architectures and design patterns if they're learning idioms. And don't waste an expert's time nitpicking over minutia. Address them at their level. Make them think critically about the choices that they're making. If you must address items beneath their level, treat those items like the trivia they are. And if you're going to address items above their letter, you're leading them. And if you're leading them, provide leadership rather than trying to provoke discussion. As an aside, where they're at is usually something you can assess by looking at what do they need the most help with. Also, relevance is important, but so is focus. Choose the important things to discuss. Importance can be decided based on a lot of different factors. Maybe an improvement is important to the hygiene of the code base, or maybe it's important to the programmer's development, or maybe it just offers an opportunity for an interesting discussion. But be sparing with your comments. In composition workshops, they usually adopt this. You should pick 10 highlights and 10 suggestions as a typical rule of thumb. It's a little awkward for code since diffs vary pretty dramatically in scope, but I like to use the guideline of response to my code review. Probably should not take them longer than my code review took me. Sometimes you can do that, sometimes you can't, but as a rule of thumb. Also, be even-handed. That rule about 10 strengths and 10 things to improve is not just about scope. People respond better to positive reinforcement than negative reinforcement, so try to identify strengths as well as weaknesses. You try to match them, one opportunity for improvement, one positive thing to say, you'll find pretty quickly you get better at spotting things you like about other people's code. And while you're looking for improvements, it's important to be constructive. This is important for everything, not just code review. People respond very poorly to criticism. Criticism is when you tell people what they're doing wrong. Criticism triggers defensiveness, even in people who take criticism well. There's lots of experimental evidence backing this up. People respond pretty well when you offer constructive suggestions, though. Constructive suggestions are when you tell people what they can do better. So be constructive. This is wrong will just make people mad. Have you considered this? Will open up a discussion. Being curious helps here, and it also helps to remember that this is your peer. Assume that they're being diligent and they have good intentions. I think that's also, don't be an asshole. Like everything else we're talking about, giving code reviews that help other programmers grow is something you get better at with practice. When it's done well, code review becomes a key mentorship activity. facilitates a round of guided revision that helps steer the programmer's development. So we talked about how the process of coding is a process of revision. We talked about how repeated efforts at revision develop coding skill. We've talked about how code review can be used to help guide the revision process to accelerate development. Now let's talk about revising the code base itself. Glibly, we can define technical debt as the sum total of all the things you wish you'd done differently. More directly, technical debt is everything about your code base that makes it difficult to extend and modify. But let's pursue that first point a little further. Technical debt generally accrues when you either accept a certain amount of poor design, which happens, or it accrues when you make poor choices when selecting idioms or abstractions or patterns of what happened, which also happen, or it accrues when you mispredicted the future and chose the wrong side of a trade-off, which also happens. It's inevitable. Technical debt is inevitable. It's inevitable from a couple of different directions. Firstly, nobody has perfect forward knowledge of the code base and what it will need to become. You can't know how to make every trade-off, and sometimes you'll need to make a call. And secondly, everybody's still getting better at coding. Not even gurus write perfect code, and they don't even know for sure what the ideal code might be. In fact, what's ideal today will probably be legacy at some point in the future. And that's before you even consider the emergencies. Product needs a feature to launch fast, we grit our teeth and we do it. Some project just needs to die, so we push it out with known flaws. These things happen to everyone, and there's no shame in it, or, you shouldn't do it. Yeah, we're all ashamed. But no matter how hard you resist, you will have technical debt. You need a plan to deal with it. So there are a number of fronts on which you can fight technical debt, and I recommend committing to all of them. The most common strategy is to limit the amount of technical debt you create. To do this, you delegate design and coding tasks according to level of expertise. The gurus and masters are tasked with architecture, initiates are given subsystems. They often have some apprentices in there helping them build them out. The apprentices, in turn, are provided with discrete and well-defined problems to explore. Every organization I've been a part of does this to some degree or another, and its effectiveness depends a lot on how your organization is staffed. It also has some potential, if pursued too aggressively, to really limit the growth of your people, right? It's still a good idea. There's no sense in asking the intern to design your critical systems, but moderation. Prevention can really only do so much anyway. You're going to have to plan for remediation. You will need a cure. Dealing with technical debt is essentially establishing a revision process for the whole code base. And here again, I see two main avenues of attack. The first approach is scoping technical debt into feature work. Doing so is taking a very responsible approach to software. The Boy Scouts have a principle where you always leave the campsite cleaner than you found it, because it's irresponsible to do otherwise. And that's the way we need to treat our code base. You go in there and you leave it cleaner than you found it, because it's irresponsible to do otherwise. However, this does have some shortcomings. It can make the features you work on prohibitively expensive. Sometimes, when you scope in the cleanup work, the product team decides that feature's too expensive, and they just scrap it. So now there's no feature and no cleanup. It can often be tempting to back down here, but you got to consider creatively reframing the problem. Can you do the most important pieces of cleanup? Can you clean it up in phases? Generally, you don't want to double the size of feature with cleanup tasks. And trying not to exceed 1.5 times is probably the right goal. But then sometimes there's no way forward but through, and that's when you have to find out how much your business team loves you. The other big problem with cleaning as you go is that you only fix what you're working on. Say you finish a big initiative, the ideas are still fresh, there's a list of things to improve, but now the team's building something else. Maybe a year or more before you revisit this. All that knowledge goes stale. Similarly, sometimes a particular chunk of code keeps kicking out bugs like some kind of reverse roach motel, and you need to get in and refactor that, or it's just going to keep presenting problems. So, in those cases, you're not going to be able to just fix what comes up next. And you need, sometimes it's just that sometimes the code that is causing you the most trouble isn't the code that you're directly working on next. And that's where the second avenue of remediation comes in. We build in maintenance time. Now, like some perverse binary tree interview problem, there's a couple ways to do this too. I think of them as the ideal way and the pragmatic way. The ideal way prioritizes each improvement against upcoming future work. Priorities are negotiated with all the stakeholders, and we explain the cost-benefit analysis of our technical debt work to product management very clearly. Then we get a single prioritized backlog out of that. This is ridiculously hard to do because there are different stakeholders and because each has a vastly different value proposition. It's like teaching cider fans and OJ drinkers to compare apples and oranges, and it's hard work understanding each other's perspective. Technical debt frequently has this long-range ROI that's hard to quantify. The payoff is a reduction in the complexity of the code base, which in turn affects velocity. Product representatives have a tough time measuring that against the ROA model used for features, which is usually measured in dollars. So usually they punt, and we end up on approach 2, which is a fixed maintenance budget. Most organizations have no trouble supporting between 20 and 30% to cover maintenance. Usually, maintenance includes resolution of product bugs as well as resolving technical debt. Teams might like to keep these two line items separate. I would recommend no less than 10% for technical debt, though. And personally, I prefer having the larger bucket to split up according to my current priority, but your mileage may vary. So, in a curious as above, so below situation, we see that revision drives software. Small cycles of revision power the developer's coding process. Code review leverages the larger cycles of detailed feedback and revision to help develop programmers. And the largest cycles of revision operate on the code base itself, where a whole team learns to collaboratively revise the collective project. At each level of this process of revision, practice and feedback increase the effectiveness of the individual, the team, and the effort. And perhaps most importantly, insights into good revision practices obtained at any level can be repurposed in the other activities. Right. So what are those good revision practices then, right? So this one is kind of key. The more you look back at your code to change it in light of what you've recently learned, the more you learn. The more you consider code you're working on as an opportunity to clean up, the more you'll clean. And seriously, this is the place where most people fall down. This is the place where most revision habits just suck. It's that people don't bother to revise. So another thing is about being self-critical. And I know I said a thing a few minutes ago about criticism, and it's true. You shouldn't just criticize yourself or anyone else and then just stop. But it's important to look back at what you're doing with a critical eye. What are the assumptions you made? And do they still hold? Was that abstraction really right? Are you holding on to a cute or clever idea because you love it and not because it makes things better? Were you lazy about error checking? When the answer is yes, move on to the constructive next step. Fix it. But police yourself, because your code reviewer is not your maid, and having a tech debt process isn't a free pass. And my third tip is actually realize, yeah, I duplicated this slide. I'm pretty sure you nodded along the first time, but blew me off. Because seriously, this is the main thing you have to do. The secret to becoming a better coder is aggressively revising your code. And the secret to successfully revising is to actually revise. How simple is that? Thanks.